On a ridge above Snowmass Village, Colorado, there is a working reservoir that looks like dozens of others scattered across the Rockies. Water goes in, water goes out. Nothing about it suggests anything unusual, but beneath its surface sits a sealed ancient lake bed, untouched for tens of thousands of years, holding one of the richest Ice Age records ever found in North America. A bulldozer operator found it completely by accident on a deadline, with a $10.5 million dam scheduled to seal the reservoir shut within a year, this time permanently. What came out of that mud during the single year researchers had to work still has not been fully explained. Before any of this became a scientific site, it was simply a small dam on private land, built in 1961 to hold back a shallow meadow drainage and form a modest private lake. It stayed that way for decades, unremarkable, until the Snowmass Water and Sanitation District purchased the water rights in 2010 and moved forward with a routine expansion, the kind of infrastructure project that happens quietly, without headlines, in mountain towns across the American West every year. On the afternoon of October 14, 2010, a third-generation bulldozer operator named Jesse Steele was pushing lake mud along the expanded perimeter of the reservoir when his blade struck something that was not mud. He stopped the machine, climbed down, and looked at what had come up out of the ground, a series of large bones, part of a tusk. Think about what that moment actually required. This was a man who had likely cleared ground exactly like this hundreds of times before, moving dirt for a living, and something in what came up under his blade told him immediately that this was different. He recognized the bones as possibly significant, and instead of pushing forward and burying them again under the next pass, he stopped and brought them directly to the project foreman, Kent Olson. That single decision set off a chain of events that moved with genuine urgency. Olson took the bones home that evening and, using nothing more sophisticated than internet sources, identified them as belonging to a mammoth. The following morning, the district manager for the Snowmass Water and Sanitation District contacted the Colorado Geological Survey. The Colorado Geological Survey contacted the Denver Museum of Nature and Science. Within days, a full team from the museum was on site, standing on ground that, until that week, had simply been the edge of a construction project. What they found in those first weeks established two things at once, and both of them mattered enormously for everything that followed. The site itself was extraordinary, and the clock was already running, because this was never research land with an open, indefinite timeline attached to it. This was the footprint of a municipal water infrastructure project, serving a growing ski resort community that genuinely needed the water it was built to hold. Even in those very first days on site, the museum team could already see, in the layers construction had barely touched, that they were looking at something the American West had simply never produced before at this scale, this depth, or this level of preservation. And that recognition arrived paired immediately with a hard deadline. Neither the museum nor the district had any real power to move. A dam still had to be finished. A reservoir still had to be filled. Every single fossil sitting in the ground beneath that construction footprint that was not recovered before the water rose again would be sealed underwater, permanently, exactly the way the ancient lake itself had sealed everything inside it for well over 100,000 years before Jesse Steele's blade ever touched the surface. The museum and the district would have to reach an agreement fast, one with genuinely no real precedent in American paleontology at this scale before that window closed for good. Here is exactly what that agreement actually meant in practical terms. A $10.5 million dam was under a contractual obligation to reach completion by mid-October of 2011, with the reservoir behind it expected to be full by that November. That deadline was not negotiable in any meaningful sense. It belonged to a working water utility serving a real community, not to a research institution operating on its own schedule. Every fossil still sitting in the ground when that water rose would be gone from scientific access forever, sealed beneath permanent infrastructure rather than natural sediment. So the museum and the district reached an arrangement that had genuinely no real precedent in American paleontology at this scale. Excavation would proceed directly alongside construction, the two operations sharing the exact same ground at the exact same time. Paleontologists working with trowels and brushes in one section, while heavy machinery continued moving earth in another, both racing against the same fixed date on the calendar. The work itself came in two distinct pushes. The fall of 2010 gave researchers only 2 weeks before the site had to close entirely for winter. At an elevation of roughly 2,700 meters, sustained fieldwork through a Rocky Mountain winter was simply not physically possible, no matter how urgent the science underneath that ground had become. The site reopened on May 15, 2011, and what followed over the next 7 weeks, running through the 4th of July, turned into one of the largest and fastest fossil excavation operations ever conducted anywhere in North America. Think about the scale of what that actually required to organize in that short a window. The Denver Museum of Nature and Science coordinated scientists and volunteers from at least 19 separate institutions. Over 380 people participated across the full length of the dig. Together, they hand-shoveled more than 7,000 cubic yards of sediment, working by hand through material that a bulldozer could have cleared in a fraction of the time, because hand tools were the only method careful enough not to destroy what was buried inside it. And alongside the paleontologists themselves, volunteers took on a role that genuinely did not exist anywhere else in American fieldwork at this scale. They called themselves blade runners, and their entire job was walking directly beside active, moving bulldozers, watching every pass of freshly turned earth in real time for the faintest sign of bone, then signaling the operator to stop the instant something appeared. Science and heavy construction, moving across the same ground in the same hours, neither one able to simply wait for the other to finish. Over 69 total working days spread across those two separate seasons. That combination of urgency, hand labor, and genuinely improvised methodology produced something nobody fully expected going in. What came up out of that ground, piece by piece, bucket by bucket, would turn out to be one of the richest single fossil sites ever assembled anywhere in North America, recovered under a deadline that never once slowed down to accommodate it. By the time the final season closed, the numbers coming out of that ground were genuinely difficult to process all at once, so it is worth taking them one piece at a time. More than 5,000 large bones, more than 22,000 small bones, roughly 50 different vertebrate species represented across the full site, more than 100 species of fossil invertebrates, more than 100 species of fossil plants. That is not simply a large fossil site. That is an entire ecosystem, pulled out of the ground almost intact, piece by careful piece. The mastodon material alone deserves its own moment of attention. More than 3,000 individual bones, representing at least 35 separate individuals, ranging from newborn calves to fully grown adults of both sexes. That makes this the largest single-site collection of American mastodon material ever assembled anywhere. To put that number in real perspective, before this excavation began, the entire state of Colorado had produced a grand total of exactly 3 mastodon specimens across its entire recorded history. The Ziegler Reservoir Basin alone held more than 10 times that number, sitting quietly beneath a few meters of mud the whole time. Among those mastodons was the largest individual ever recorded for the species, nicknamed by the excavation crew for the portable toilets that happened to be sitting directly above where its bones were finally uncovered. And the mastodons were far from alone down there. Alongside them, the team recovered material from 4 separate Columbian mammoths, giant ground sloths, ice age camels, and horses, a bison specimen nearly twice the size of any bison alive today, black bears, coyotes, bighorn sheep, otters, muskrats, minks, and beavers, salamanders, frogs, lizards, snakes, fish, and birds. And one particular deer skeleton, dated to roughly 70,000 years ago, roughly 10% larger than any modern deer species with a distinctly different dental arrangement, different enough that researchers have genuinely considered whether it represents a species science has not formally recognized before. But the raw number of species, as extraordinary as it already is not actually the detail that stunned the research team most. What genuinely surprised them was the condition everything had been preserved in. Leaves recovered from the sediment were still green after more than 100,000 years underground. Beetle wing cases still carried their original iridescent shine. Fossil conifer cones remained fully structurally intact, not crushed or flattened by the weight of everything above them. And in one section of the ancient lakeshore, researchers uncovered a 20-meter stretch of driftwood logs, still lying almost exactly where they had originally come to rest, undisturbed for tens of thousands of years. That level of preservation was not an accident of luck. It came directly from the lake sediment itself, which had acted as a nearly perfect seal against oxygen, slowing decomposition down to a rate standard field protocols were simply never designed to encounter in the first place. But the real value of this site was never really about the bones themselves, remarkable as every single one of them genuinely is. It was about what the layers of mud surrounding those bones had been quietly recording, year after year, for tens of thousands of years before anyone ever knew to look. Most fossil sites, anywhere in the world, capture a single frozen instant in time. An animal wanders into a tar pit and never comes back out. A riverbank suddenly collapses. A flash flood sweeps through and deposits a scattered layer of bone and debris in one violent afternoon. What survives from moments like that is essentially a cross-section, a narrow window covering at best a few centuries. Scientists studying sites like that are left extrapolating outward from one frozen slice of time toward everything else that must have surrounded it, without ever actually seeing the surrounding picture directly. The ancient lake at Snowmass did not work that way at all. What it preserved was not a single moment. It was a sequence, nearly continuous, carefully stratified, and chronologically ordered, spanning roughly 85,000 years of uninterrupted ecological time. Each thin band of sediment recorded its own specific year, its own specific set of conditions. Which plants were growing directly around the lake, which insects were present in that particular season, which animals were coming down to the water to drink, and what the climate itself was actually doing at that exact elevation while all of it was quietly unfolding above the mud. Think about what that actually means for researchers trying to reconstruct the deep past. This was not a photograph. It was closer to a continuous recording, laid down grain by grain, year after year, for longer than the entire span of recorded human civilization, repeated nearly 17 times over. Here is exactly why that record mattered so much to science the moment researchers understood what they were holding. The sedimentary sequence at Ziegler Reservoir spans roughly 140,000 years ago down to approximately 55,000 years ago, covering the tail end of one major climate stage, the entirety of the following one, which includes the last interglacial period, and continuing on into the beginning of the colder stage that followed it. Before this specific site existed as a known scientific resource, there was no well-dated, high-elevation, multi-proxy terrestrial record of North American ecosystems covering that exact interglacial window anywhere in the existing scientific literature. None at all. What researchers previously understood about that period came almost entirely from deep-sea cores pulled from ocean floors, ice cores drilled out of polar regions, and a scattered handful of low-elevation sites, none of which could actually speak to what was happening specifically inside a high-mountain ecosystem during that same stretch of time. Alpine environments during the last interglacial were, in the strictest possible sense, essentially undocumented anywhere on the continent. The Ziegler Reservoir sediments changed that gap entirely, and they did it through something as small and as easy to overlook as individual grains of pollen, settling silently into mud year after year for tens of thousands of years, waiting for anyone to finally notice they were there. Because it turns out that pollen alone, examined carefully enough and read in its proper sequence, could tell an entire detailed climate story completely on its own, one season at a time, stretching back further than almost anything else recovered from that same stretch of the Rocky Mountains. Read carefully. The pollen record from Ziegler Reservoir tells a genuinely detailed story about a landscape transforming itself over and over across tens of thousands of years. During the peak warmth of the last interglacial, roughly 130,000 to 120,000 years ago, when global temperatures and sea levels actually sat higher than they do today, the pollen sequence shows a rapid, unmistakable shift from open alpine conditions into genuine forest. Spruce expanded first, pine and Douglas fir followed close behind, And then, remarkably, oak pollen appears in the record, direct evidence that warming at this specific elevation was strong enough to support broadleaf trees in a place where, today, only conifers managed to survive at all. As that same climate cycle moved into its colder phases, the pollen record shows the forest retreating just as clearly as it had once expanded, sagebrush steppe reestablishing itself around the lake shore. And by the time the following glacial stage brought full cold conditions back to the ridge, the vegetation had returned completely to alpine tundra, closing the loop on a single, complete climate cycle written directly into the mud. Here is where the story becomes genuinely remarkable, because the animal fossils buried in those same exact layers do not simply sit there as a random, uniform mix. They map directly onto that same vegetation record, almost as if the two were designed to be read together. Mastodon remains, more than 3,000 individual bones representing at least 35 separate animals, are concentrated specifically in the older, deeper layers, the ones corresponding to the warmest phases of that interglacial, precisely when the pollen record shows real forest cover surrounding the lake. That placement is not a coincidence. Mastodons were browsers by nature, built with low-crowned molars designed specifically for processing woody vegetation, leaves, and shrubs, not open grassland. Finding their remains concentrated exactly where the forest pollen says forest actually stood is a correlation the site itself makes directly visible, sitting right there in the layered stone. The Columbian mammoths tell an entirely different story from a different set of layers entirely. Their remains cluster instead in younger sediment, dating from roughly 80,000 down to 55,000 years ago, the period after that interglacial warmth had already passed, when the pollen record shows open, cooler grassland reestablishing itself around the lake. Mammoths were grazers, built with flat-ridged molars adapted specifically for processing grasses rather than woody browse, and their position in the layers, sitting directly above the mastodons, maps precisely onto the exact ecological conditions those animals actually required to survive there. And then there is the gap. In the layers corresponding to the coldest phase sitting between those two warmer periods, there is almost nothing at all, neither browsers nor grazers. The pollen record confirms the vegetation around the lake at that exact moment was cold sagebrush steppe, and the fossil record confirms it independently. The forest-dwelling animals had already left. The grassland animals had not yet arrived. For that narrow stretch of time, the lake simply recorded silence in both its pollen and its bones, and nobody on Earth knew that silence was sitting there, preserved, until this exact site was finally opened. Among everything recovered from Ziegler Reservoir, one specific kind of fossil could be read almost like a calendar, year by year, and it came from a place nobody would immediately expect: the tusks themselves. Tusks grow continuously throughout an animal's entire life, laying down thin bands of dentin in a pattern that records seasonal variation in growth rate, in diet, and in physiological stress, one narrow layer at a time. Cut a tusk open along its full length and examine the cross-section under magnification, and those bands appear as alternating dark and light rings, annual increments that can be counted, measured, and chemically analyzed in essentially the same way a dendrochronologist reads growth rings inside a tree trunk. Each individual band carries real information: how fast the animal was growing that particular year, whether it was under nutritional stress at the time, roughly when in the calendar year it finally reached full biological maturity. Researcher Daniel Fissure, who had already spent decades developing exactly this method on mastodon and mammoth material from sites across the Great Lakes region and Siberia, turned his attention specifically to mastodon tusks recovered from snowmass dating to the interval between roughly 140,000 and 100,000 years ago. That window covers precisely the period the pollen and fossil record had already established as a major climate transition, moving directly out of the warmth of the last interglacial and into the onset of the colder period that followed it. Given the scale of that documented climate shift, the reasonable expectation going in was that the tusk growth record would show real environmental stress, narrowing growth bands as conditions worsened, disrupted seasonal patterns, visible signs of nutritional pressure building as the colder phases set in around them. What the analysis actually found instead was something genuinely unexpected. Growth rates stayed essentially stable across that entire interval, start to finish. These mastodons had, in the language of the research itself, simply coped. They persisted through the full range of climate variation documented directly in the lake sediments surrounding them, maintaining consistent growth patterns from the warmest peak of the interglacial straight through the transition into colder conditions, without the kind of physiological disruption researchers had genuinely expected to see in an animal being pushed toward the outer edge of what it could actually tolerate. Paleobotanist Ian Miller, summarizing that Tusk data alongside the site's broader results, put it about as plainly as the science allows. The mastodons simply kept going, doing just as well at the end of that long climate transition as they had at the very beginning of it, despite the world around them changing substantially the entire time. That finding does not mean climate change was somehow irrelevant to these animals' survival more broadly. What it does mean is that this specific shift, across this specific span of time, documented in this specific lake, never actually pushed Snowmass's mastodon population anywhere close to its real biological limit. It is a genuinely useful piece of data inside a much larger ongoing scientific debate about what eventually did end the Ice Age megafauna for good, a debate this site clearly contributed real evidence to, without ever fully resolving it on its own. And that same layer of sediment, it turns out, was holding on to something else entirely, a set of marks nobody excavating that ground could actually agree on the meaning of. This site never needed a solved mystery to matter. It handed science an unbroken 85,000-year record, linking climate, vegetation, animals, and fire at an elevation nobody had ever documented that precisely before. But it also closed one door forever. Whatever those parallel incisions and strange rock placements actually meant, whatever a second season of careful excavation might eventually have revealed, is now sitting under permanent reservoir water, exactly the way the mountain itself sealed this basin the first time. Thousands of centuries ago. The bones are safe in a museum. The question underneath them is not. Subscribe for the next investigation, and I will see you in the next one.